Happy day and welcome everyone. Today's lesson is on Hess's law of heat summation. When is this useful? Well, a lot of times we can look at a balanced equation. We can theoretically take a look at a thermochemical chart and be able to figure out products minus reactants and figure out how much energy is either absorbed or released for a particular reaction. And it can really be any reaction. But what happens when you look at the chart, for example, in this situation, where we've got boron, this diborane, that is highly reactive. They actually had considered using it for rocket fuel. If I take a look at the thermo chart here, I see barium, I see beryllium, I see bromine. I don't actually see boron. Boron should have been right inside of there, and I'm not seeing it. And in addition to that, I can't really just run this reaction in a calorimeter. This is explosive, okay? So what I can do instead is I can figure out if I've got some intermediate reactions, as long as these reactions can be manipulated to work out so that it ends up equaling what I'm going to call my target reaction. Then all I need to do is simply add up my delta HF values, okay? And so that's really all that we're talking about here with Hess's law of heat summation. So what Hess's law states is the overall enthalpy change for a reaction is equal to the sum of. So all you're going to do is you're going to add up all of the enthalpy changes for what are called the individual steps or the intermediate steps in the reaction. So this is kind of where the books can lead us and say, you know, what do we do? How do we do it? But in reality, the best thing to do is actually just to watch it done, okay? And so that's going to be the fastest thing. So I'm going to take you really quickly, since we did this problem on diamond, and so this one was pretty simple here because we only had two lines in the of intermediates. And so again, what we're trying to do is manipulate line A and line B so that I can add up my reactions so they equal my target, okay? And so I can see that what I did when I figured out the stoichiometry here is I can see that the CO2's canceled out and the O2's canceled out. What was I left with after I manipulated them? That carbon diamond yields carbon graphite, which is exactly what I wanted for the target. And when I added up those numbers, I got a negative 1.88 kilojoules, telling me that that was the amount of heat that was released. Now, I want to make sure that you understand it doesn't actually tell you anything about time. It just gives you what the energy change is. Okay, I think this is a great time to be able to watch a quick little clip here on diamonds. And the question is, are diamonds forever? But just to get a little bit of an understanding as to what the forms of carbon could be. Let's take a listen.
It may be hard to believe that the graphite in your pencil is made of the same stuff as these diamonds. But carbon is an element with many guises, including all living creatures. When an element, like carbon, exists in several natural forms, each form is called an allotrope. One of the best known carbon allotropes is diamond, the hardest of all natural materials, and among the most beautiful. Diamonds begin at least 100 miles underground. There, pressure 5,000 times greater than surface pressure and temperatures nearly hot enough to melt iron transform carbon into diamonds. And there they stay, until blown to the surface by the spew of a particular kind of volcanic eruption, a kimberlite eruption. The last diamond-spitting eruption happened over 100 million years ago, leaving its plumbing, known as kimberlite pipes, as evidence. But finding the pipes, hidden by time and erosion, is no small task. Geologists employ odd comrades in the search. In this case, termites. In the process of building these impressive mounds, termites excavate rocks and minerals that may or may not suggest a cache of diamonds below. In the 1960s, geologists discovered one of the richest kimberlite pipes in Africa, with a little help from termites. Once the mining begins, Earth moving on a termite scale seems completely insignificant. 85 tons of rock are blasted, crushed, and processed to produce a single handful of gems. At the Finch mine in South Africa, miners have been digging for 30 years. This hole is 2,500 feet wide and 1,200 feet deep. Inside a cut diamond, light is split and facets create rainbows. But the sought-after gem is nothing more than pressure-packed carbon atoms. The tight crystal structure makes diamonds hard as well as beautiful. In a single year, 3.5 million tons of rock are blasted, crushed, and extracted, all for tiny pieces of pressurized carbon. Only 20% of the diamonds unearthed make the grade as gems. And after all that, it turns out that diamonds are not forever. In several million years, these hard-won gems will disintegrate.
I always find it great to kind of relate things to our everyday lives, so just kind of nice to be able to see and get a little bit of history as to how we come about wearing these diamonds. Okay, so on Q14, we've got another target equation, and so this is going to be my target right here. And then I'm given two intermediate reactions. So again, what you can do is you can do products minus reactants. This one should be pretty easy to do, where if you go to the thermo chart, you can figure that out. But a lot of times what the AP does is A, they might not give you that, or B, they'll give you numbers that are slightly different. And if that's the case, you're just going to have to do the Hess's law of heat summation. And usually there's something that's unknown, so you wouldn't be able to do that. Okay. So I'm going to take a look, and I am going to try to find one thing in each of the intermediate steps that only appears in my target, okay? So only one thing. So if I look at this, I'm going to start with the 4NH3, and that doesn't appear in my target. The 5O2, well, the O2 does appear, but the only thing is it also appears in line 2, so don't touch it, okay? You're looking for one thing that only appears in the target. The 6H2O liquid, that doesn't even appear at all. And then the NO, yes, very good. So I'm going to use a circle on this, and I'm going to use a circle on this. Two things I need to check. One thing is the side it's on, reactant or product. So if your target, that substance is on the product side, and it's on the reactant side in the intermediate, flip it. Okay, you're just going to reverse it. And you don't want to change your target equation. That's what you're trying to find the delta H for. You're actually going to change your intermediate, okay? So in this case, and then I also want to look at the coefficient. So those two things. Well, it looks like on the product side is where my NO, my nitrogen monoxide, is in my target, and it is in my intermediate as well, but the coefficient is different. This is times 4, which means I'm going to need to divide this by 2 to make it the same. Okay, again, notice I didn't touch any other substance. I'm assuming that just by doing that one change, everything else is going to follow suit. Okay. So now in the next line, again, no 4NH3s, no O2, leave it alone. The N2, yes, the N2 is good. So I'm going to use a triangle here. Again, it doesn't really matter what shape you use. You can use stars or whatever you want to, whatever you're feeling. And there's my N2 there. Check the side. Oh, that's on the reactant side, but it's on the product side of my intermediate, which means I'm going to need to reverse it. Now, in addition to that, there's only 1 mole in my target equation, but it's times 2, which means I'm going to need to divide by 2 again. Okay, and so people will either say I'm going to multiply by 1/2 or divide by 2. It's the same thing. Okay, you can do either one. All right, so let me give you the shortcut real quick here. So the shortcut is that I don't actually do anything else besides what I just said I was going to do. And so I get a negative 306.5 here. And then I am going to do the 790 divided by 2, which is 395. But I also need to reverse it. And if you reverse it, you get a positive 395. Now, once I have these two numbers, all I'm going to do is add them up. It's called Hess's law of heat summation. So I'm going to add my 395 plus my negative 306.5, and my final answer is positive 88.5 kilojoules. Okay, and so then I would say I'm done, I'm all set, it's a multiple choice problem, good to go. Now, what if the wording is show or prove that the stoichiometry works? So now what I'm going to do is I'm going to tell exactly what I needed to do. I start off by writing a target line. So this is going to be like my sum line. And so I'm going to put my arrows. I always like to line up my arrows first, so that way it makes it a lot easier when you go to cancel things out. So I have N2 plus O2 yields 2NO. So that's my target reaction. That's what I want it to equal. So now is exactly what I had said for that top line. I'm simply going to divide it by 2. So instead of 4NH3, it's going to be 2NH3 gas. Now the phase does matter. Plus 5 halves, so I'm just dividing it by 2. 5 halves oxygen gas. Then my arrow. So now I've got 3 water liquid, 3 H2O liquid, plus 2 NO gas. Okay, and now on my second line, I'm going to have to reverse it and divide it by 2 at the same time. Okay, so I'm going to start with the products and divide it by 2. So I'm going to get N2 gas, 1, N2 gas, plus 3 H2O liquid. Then to the right, I'm flipping this, I'm going to get 2 NH3 gas, plus 3 halves O2 gas. Okay, fun part. Get rid of your spectators. Okay, so we want the 2 that look exactly the same. Now, again, what normally would happen is you would write all of these under the sum line. So all 8 of these would be written under the sum line. And then you would look at it more like we do with NIE and cancel out on both sides. But it's a lot faster if you just do it right now. Okay, why do that? There's no reason. It's still showing the stoichiometry. So I can see that my 2 NH3s cancel out right there. I can also see that my 3 H2O liquids cancel out. Okay, now here's a weird thing. I can see that my O2 is different. On this side, I have 5 halves, and on this side, I have 3 halves. Well, if you subtract 5 halves minus the 3 halves, you get 2 halves, and 2 halves is the same thing as 1. So actually, I can cancel out the 3 halves, and when I do that, I am simply left with 1 oxygen. Perfect, because I've got N2, which checks right there. I have my 1 O2, which checks right there, and my 2 NO gas, which checks right there. Okay, let's try the next problem here. All right, so the next one says, they're giving us this conversion again. Write the equation for the formations of each of their elements in their standard states, then calculate the delta H of the reaction. The AP does this. This is a very, very common setup of a problem. So part A and B maybe would be, or part A might just be, write the equation for the formation of each of the following, okay? All right, so let's do this first. So I've got this C4H4S liquid, so let's start with that right there. And then I also have the C4H6 S liquid. Okay, so when I go to write these, I'm going to put my arrow in here, and I'm trying to make C4H4S liquid. Okay, well, what elements make that up? Well, that's pretty easy. Carbon, but remember, it would have to be in the graphite form because it has to be a 0. Plus hydrogen, but remember hydrogen is H2 gas in its natural form. And then sulfur is just going to be an S, is going to be what we're going to be using for sulfur, a sulfur solid, okay? And so if you're not sure, you can take a look at the thermo chart to check to see how it has a value of 0. Okay, now, only thing is I need to balance it, so then that means that I need a 4 in front of the carbon, and I need a 2 in front of the hydrogen, and now it's balanced, okay? And they tell me that the delta H for this reaction is a positive 53.1 kilojoules, right? Let's do the next one. So now this one's C4H6S liquid, same exact thing here. I've got carbon in the graphite form, plus hydrogen gas, plus sulfur solid. Okay, let's balance it. Well, I need 4 of this, but now I have 6 hydrogens, so I'm going to need a 3 in front of there. And this one, they say, is a positive 80.3 kilojoules, and that is for a 1 mole. They're giving us the heat of formation for 1 mole, and beautiful because when I balance these, it is actually representing 1 mole of each one of those. So I don't have to change anything. I don't have to multiply or divide or anything like that. It's good to go. Okay, so now I am going to circle, square, triangle this whole thing, all right? So I'm going to take a look at my target right here. Here's my target. And looking for one thing in each of these intermediates to be able to match up with my target. So I don't see carbon in my target, not there. I do see hydrogen, but again, tricky. Hydrogen also appears on my second line, so leave it in my second intermediate. I don't see sulfur in there. Oh, there we go. C4H4, so S, so that's this one right here. And then I see the C4H6S in the bottom one because they're all the same, so I already went through this. And that one is right there. Okay, now notice I'm matching my intermediates to go with my target. It's not the other way around. I'm not looking for hydrogen. I'm not looking for H2 or looking for the C4H4S. I'm not looking for that. I'm going through my intermediates to check to see if I can find if it matches in my target. If not, you're going to have to save it for last. If there's nothing in that line, then save it for last, okay? All right, so now let me go ahead and write out what my values would be and how it would change. So C4H4S in this first situation, I can see it's on the wrong side. So I'm going to have to reverse this one. And the bottom one is correct. 1 mole, and it's on the product side. So I'm going to do nothing to that line. Okay, so if all I needed was the delta H and I didn't have to show the stoichiometry, then in this case I would simply say it's negative 53.1 kilojoules and a positive 80.3 kilojoules, and then I simply have to add these together and I get a positive 27.2 kilojoules, and that is my delta H for this target reaction here. Okay, that's what that's representing. Now again, what if they ask you and they say, nope, not enough, show us that the stoichiometry works? Okay, fine. So what I'm going to do is, again, I like to line up my arrows here, and then I'm going to write my target equation down here, plus my H2 gas, and gives me C4H6S in the liquid form. Okay, so I'm going to do what I said I was going to do to each of these reactions here. So this first one is simply reversed. So I'm going to do the C4H4S liquid is on this side, but on the right side, I have my 4 carbon solid plus my 2 H2 gas plus my sulfur solid. And the bottom one, I did nothing to. So I'm going to rewrite it exactly as is. 4 carbon graphite plus 3 H2 gas plus my sulfur solid gives me C4H6S liquid. And so now, here we go, fun part, cross off the ones that look exactly the same. So it's kind of like the spectator ion thing, okay? So I see that the 4 carbon solid graphite right there and there, those are going to cross off. I also see my sulfur solid on either side, cross those off. And then I see 3H2 and 2H2 on the other side. Well, that means that 2 of them will cancel out. So let's cross 2 of them out. Well, what that means is I'm actually left with 1. 3 minus 2 is going to give me 1. Perfect, because again, I see that I'm left with the C4H6S, which checks right there. I'm left with 1 hydrogen, which checks right there. And I'm left with the C4H6S, which checks right there. Okay. All right, last one. Hardest of them all, okay? And so this one tends to be a little bit tricky. And I do want to mention that usually you're not given anything extra, okay? But sometimes you are. The other thing that I want to make sure, a lot of times the problems, what they'll do is they will assume that you know that if it's an element in its standard state, that it has a value of 0 as its heat of formation. So sometimes they'll do things where people will start looking and they're like, I wasn't given a chart. What am I supposed to do? Well, assume that it's 0. Okay, here we go. So again, if I can do products minus reactants, great. You should be able to get the same answer, okay? Because that's a theoretical value, and so is this. You should be able to get the same exact answer. So, but obviously in this situation, they're asking us to solve it stoichiometrically here to figure it out. Okay, so here we go. I am going to just use my circle, squares, and triangles because all the equations are given to me. So in this top line, right away, I see this boron solid and it appears in my target reaction. But I just need to make sure it doesn't exist in lines B, C, or D, and I don't see it anywhere else. Good. So I'm going to mark this one here, and I'm going to mark it right there. Okay, so the 2 boron solid. All right, so now I have the next line, line B. So again, I'm only finding one thing that matches. The B2H6 gas. Oh, look, B2H6 gas. I see it in my target. I don't see it anywhere else. Again, I'm double checking to make sure it doesn't appear anywhere else, and it doesn't. So again, I can use a triangle or a square or whatever you want. I'm just going to use the triangle here, okay? So that matches there. Line 3. Okay, the H2 gas. Oh, H2 gas. The O2 I wouldn't want to touch because it doesn't even appear in the target. The H2O liquid I also wouldn't want to touch because it doesn't appear in the target, but the H2 gas does. Okay, so let's use a star for the H2 gas. There it is, and there it is. Now, last line. The H2O liquid to H2O gas. Okay, it doesn't appear in my overall target, so maybe I can ignore it. Let's check to see what happens, okay? Because in order to ignore it, that means that I would need to make sure that these 3 lines right here is all I would need for it stoichiometrically to work, okay? So it has to equal my target. So let's check to see what happens. All right, the 2-boron solid, it's on the correct side. I will do nothing to it. Second line, my triangle here, the coefficient's the same, but it's on opposite sides. So this one I am going to reverse. Third line, my H2 gas, reactant side, great, but it's times 3. So I have 3 moles of my H2. And then the last line, I don't know what I'm doing to this yet, okay? So I'm going to put question mark here because I'm not exactly sure. I'm going to have to come back to it and figure out if I need to do anything to it. Okay, so let's go ahead and let's write these out. So I'm going to get my target line going here. So let's get a target line. And again, I am going to actually leave a space, by the way, for that last line, for that line D, just in case, because they gave it to me, so maybe I need it. All right, so my target is what I have clouded in here. So 2 boron solid plus 3 H2 gas gives me B2H6 gas. And again, we know what I'm looking for is the delta H value. Why can't I just calculate it right now? Because I actually need to figure out what I'm doing with line D first, okay? So that's why. So sometimes you can look at it and be able to figure it out, and some of you may be able to right now. I'm not gonna go into it just yet, but I will show you after, okay? Because sometimes it just confuses people. So my first line, I said I was going to do nothing to it. So it's 2 boron solid plus 3 halves O2 gas yields B2O3 solid. And my delta H is negative 1273. It stays. Second line, I said I'm going to need to reverse it. Okay, so my products become my reactants. So B2O3 solid plus 3H2O gas yields B2H6 gas plus 3O2 gas. Okay, well, if I reverse it, the only thing I'm doing is changing my sign. So that's a 20 positive 2035 instead of negative. Okay, third line. This one I said I was going to multiply everything by 3, but keep it in the same direction. So I've got 3H2 gas plus 3 halves O2 gas yields 3H2O liquid. Okay, now, if I start canceling things out, my hope is that I could end up with my final target. So let's see what happens if I start canceling things out. Well, what do I see? I see that the B2O3 solid, I can cross off right there. I see that I can cross off the 3. Okay, so this is kind of interesting. I've got 3 halves O2 and 3 halves O2. Well, 3 halves plus 3 halves is 6 halves, which is actually equal to 3. So if I add that up, then I can actually cross off my 3 O2s by saying 3 halves plus 3 halves equals 3, and so those get canceled out. Okay, let's see here. Well, I have a problem now because my water's not canceling out. You cannot cancel out gas with liquid. Wrong, you can't do it, okay? So that means that I actually need line D. So what do I need to do to line D in order to make it so that these 3H2O gas and liquid cancel out? Well, first, I can see that I need to multiply it by 3. I'm sure you're seeing that. So I know I need to multiply it by 3 so that it would be 3 of them. If I leave it as is, then what happens is I will get 3H2O liquid on the left and 3H2 gas on the right. If I do that, then they'll cancel out. That's what I want. I want them to cancel out. I don't actually want it to be added. So I'm going to keep it exactly the same way. The only thing I have to do is multiply it by 3. So let's go ahead and add that right back in. So, and by the way, on this line here, we have the 286, the negative 286 times 3, which gives us negative 858 on this one. So let's come back to that real quick. Okay, so I've got 3 water as a liquid and 3 water as a gas. So all I'm doing is multiplying that one by 3. And so then we know that 44 times 3 is going to give us 132 positive. I didn't flip it. So a positive 132 kilojoules. And now all I need to do in order to figure out what my delta H is for the entire reaction is, again, it's called Hess's law of heat summation, which means I'm going to add everything up. So when I do that, I get, please make sure that you check this yourself, okay? Don't just assume that you're going to get the same calculation. So I'm getting a positive 36, and so this is in kilojoules. And again, this is the delta H for this particular reaction, for the reaction as written. Okay. All right. And I hope that this was helpful. That's it. That's Hess's law of heat summation. You're going to need to make sure that you get some practice with this, though. This does take a little bit of practice to be able to understand. And happy day.